Now is the time for the keynote session. We have a special guest from Google today. Google was kind enough to send their best of the best to speak about how their information is handled at Google, how they organize the world's information across the globe. And I would like you all to please put your hands together to welcome Hung Lu.
Yeah. So good afternoon. It's an honor and also a challenge to accept this invitation to speak at this panel. To these people with such diversified background, and it was really scary because it's a different community and never been present the technical content too. But I have to. My boss I work for at Google is a Pakistani American. He used to be a dean of university for Pakistan. I worked for him for over 10 years. So the title of my talk today is Hardware System for Cloud and Machine Learning. I with Google for almost 17 years. Google's system and service infrastructure. I want to start with our the founder's mission 25 years ago. Our mission is to organize the world's information and make it universally accessible and useful. So this simple mission evolved over the 25 years. Now you look at it, it's still the same mission and become the big trend in the tech industry, big data, cloud, and AI. So we start from search in 1997 from a garage in Menlo Park. And the search has evolved quite a bit in the past 25 years. Now we have 3.5 billion searches per day. So we start from search in 1997, garage in Menlo Park. And over the past 25 years, search has evolved quite a bit. Now we have 3.5 billion searches per day, over 100 billion searches per month. And starting from search, we also evolved developing a lot of app application from Android, Google Maps, YouTube, Gmail, and the Google Play. So we have 8+ apps with 1 billion users. And in the past few years, we have also find opportunity to expand our footprint in Google Cloud. Now we have 1 billion individual IPs connected by Google Cloud Platform. So if you look at the cloud, it's a pretty big market with over 82 billion TAM.
Hello.
Okay. So in the past few years, in addition to the web-based app growth drivers, cloud has been the key thing for Google. It's actually the fastest growing market for Google with over 40% year-over-year. It started from cloud, we call it 1.0, where you do virtualization and share the data center with enterprises customers. So this way, you don't have to set up their own data center and can just release from the cloud. And the cloud 2.0 is instead of renting the data center, they do hardware on demand. So it's really like pay as you go. And today I need this many servers, and here you go. And more recently, the cloud has evolved from cloud 2.0 to 3.0. What is 3.0? 3.0, cloud 3.0 is no longer you are renting the server, you are actually renting the computer power, and you can do a lot of things in terms of real-time intelligence and the machine learning. And here is our, actually Google's first data center in Oregon, Dallas. You can see here, you have a data center housing. Yes, okay. Housing all the servers and all those things together. So inside, you will see this is typical building with 30 megawatts power, 60 typically around 60,000 servers and with a lot of disks 120,000 is typical number for storage. And most of all, you have network with all-to-all uniform connectivity to connect all these things together, really orchestra as a whole computer. So here's a view of what's inside the data center. You have rows of servers, and it's quite big. You can see it's rows of servers. And the next thing you can see is just thermal and the cooling. We say it's a pretty colorful Google color, but they are actually used it's actually the plumbing for cooling the data center. And the data center is more than just a building or campus scale. It's actually a global computer. Here you can see it's our global footprint with all the data centers connected together with wide area network. Okay, so how do you connect all these servers together inside the data center? It's use a pretty typical thing called closed network with aggregate bandwidth growing from 2 terabits and all the way now to 65 terabits per second. And you have a rack of servers connecting with the top rack switch to the aggregation block and all the way to the spine block. And all this is possible with, first of all, it's a centralized software control where you can control all these networking switches. And there are two key hardware building blocks. I'm proudly to be part of it. It's optical interconnects and also merchant switch silicon. So here's the evolution of Google's data center network. We start from 2006 using it's a copper cable to connect server together, a program called FireHose. And then now in 2008, we first deployed large scale optics inside the data center. It's called 10 gig SOP plus. And fast forward, now we use the 40 gig and now all the way to 400 gig optics. And then it's with a bisectional bandwidth of 6.5 petrobits per second. And this is a network at a scale that we can't buy in the market. That's why we make it ourselves. And if you look at all the optics we are using inside the data center, it's quite astonishing. We start from 10 gig and then 40 gig. And under the same footprint, we grow the bandwidth by 20x. And in the meantime, we are able to improve the power efficiency and the linear density. I want to shift the gear a little bit. Now we talk about accelerators for ML. So why we need accelerator for ML? This is really driven by two factors. Because of the slowdown of Moore's law, so you won't get the same compute power from the same silicon you had like a year ago. Before we can every 2 years we get a scale of from Moore's law. Now we don't get that, and in the meantime, the emergency of deep neural networks driving more compute power. So people start doing a develop accelerator. What is accelerator? Accelerator is driven for more efficient computing, using compute more tightly coupled with memory to move the data around. And starting from 2017, we actually have Google's machine learning case using TPU actually surpass our traditional computing use CPU. So what is a TPU, right? If you go back to the previous slides, so there are many accelerators, right? Is that you have people first start doing FPGA to make an accelerator, then NVIDIA has this GPU, and Google, we have TPU. So what is a TPU? TPU is a specialized hardware for dense matrix multiplication, which is needed for neural network calculation or computation. It has very high bandwidth, called high band HBM memory, next to the computation. So there's a lot of compute and data movement between the matrix processor and memory. And this way you can really train and train large model of machine learning, large machine learning models. And we have to use the liquid cooling starting from TPU with version 3 because there's so much power in that concentrated area. And now TPU, starting from TPU V3, we start using cooling, and now we add the TPU V4. And if you look at the one single TPU V4, it has 275 petaflops of computing, and it has 32 gigabytes of HBM memory. And the next thing is even more powerful than TPU itself. It's called the TPU supercomputers. This we use optical interconnects to scale TPU from a single computer node to thousands of nodes, and it's really becoming a large supercomputer. And if you look at starting from TPU V2, we connect 256 nodes using copper cable, using 2D Torres. So it's a relatively small scale. And the TPU V3, we connect 1,024 chips using 2D Torres. And then we use the optics in the last wraparound, so it's still limited use optics. TPU V4 pod is a full-blown of all optical interconnects. And there we connect 4,096 chips using the state-of-art optical technology. And if you look at the compute power, it's 1.1 exaflops. This is very close to the world's fastest supercomputer. And here we are able to shrink everything in a few aisles in the data center. And it has huge bisectional bandwidth, 24 terabits per second. And the computing and the networking for TPU supercomputer is different than the network we're using for cloud. Because here we have a lot of synchronous interconnect to do parameter distribution, and it requires optics with low latency and a high bandwidth. So, okay. So, what can you do with TPU supercomputers? So, machine learning training requires a lot of compute power because it has a lot of parameters. And here's a plot to show you the ML training at the scale for drawing, vision, and the language modeling. Language modeling is becoming the largest machine learning model we can possibly train on supercomputers. And actually, Google recently published a thing called PAM. It's a large language modeling through ML pathway. It has 540 bytes of bits of parameters. And if you look at the large language model scaling, it's 10x every year. This outpaces Moore's law scaling, which is 2x every generation. So this is one of the reasons we need accelerators and for these special applications. And the next thing people will ask, how do you use this supercomputer? Give me some use cases. The first one people are quite familiar is called AlphaFold. AlphaFold does not need, because it's not training, so it does not need a lot of TPUs. It's actually 128 TPU V3 cores, and it can train the model in like days. And Google's DeepMind team has already generated 200 million accurate 3D protein structures, and the database is released to the public. And in comparison, if you want to generate this many models, right, even like traditionally use the experiment way to produce this 3D protein structure, it costs millions and years to just to prevent to produce like a million, not 200 millions. So here's a very exciting thing I just talk about is called PaLM. It's a large language modeling on TPU v4 pod. This is largest language model, language training model people ever used. It's actually across two TPU v4 pods using 6,144 chips, and it takes 6 weeks to train this model. And there's between these two parts, how can you connect them together? We use pathway software to enable flexibility partition of model parameter as data parameters. So we have done all this training. What can you do with this all this training? So here's an example. I asked machine to explain a joke to me. Says, "Did you see Google just hide this thing called the TPU system? Show them how to communicate in between two different parts, and the machine model will actually respond and tell you, give you a very scientific explanation." Which I think it does a much better job than I can explain this to you. Okay. So this is my short presentation. I want to end my talk with a eulogy or a sentence I got it from my first day at the school when I first came to the United States. It's called it's from famous French camps, and he have this thing: "Fortune favors prepared mind." And with that, we Google start from a tiny search company to grow into a big giant. Do a lot of things we couldn't be able to do 25 years ago. For myself, I came to United States for grad school. Now I'm working in on the frontier of a high tech. Any questions?
For questions, there are mics on these sides that you can come to and speak. So, or you can also raise your hands. We could get the mic. There are. No, I don't think there are questions. There is. Oh, there's a microphone right here. Sorry. There's one more over there as well. Go ahead. Oh. Go.
The explanation of joke, how far that is from AI being.
I cannot hear you.
Okay, can you speak a little closer to the microphone? Sorry.
The explanation of joke you shared in the end, how far that is from AI being sentient.
The explanation of the joke you shared, how far it is from
AI being sentient.
AI
being sentient.
Insentient. So actually, there are two. I couldn't quite get your question, but I think the two hottest trend in AI. One is large language modeling. Just imagine in the future interaction you have with computer. It's not through keyboard. You talk to the computer, and the computer can talk and respond like a human being. So that's number one trend. The second trend I didn't talk about is generative AI. So you talk to the machine and just give him a list of things, they can generate a picture and a video. Did I answer your question?
Well,
closer to the microphone. We can't hear you.
I wanted you to speak to the fear that AI being, heading towards artificial general intelligence, So joke and sarcasm, all of that, these are very intricate human communication.
Another thing I can didn't explain list here as an example. I just list a joke is can help you do math problems. So you ask say I have this math problem. Talk to the machine. They can actually give you detailed explanation on how to solve challenging math problems.
That's fair.
Yeah.
Thank you. We have another question over there.
Yeah.
Hey, how are you? Something I wonder about as we look at these models being trained at the scale that they're being trained at, if that knowledge will be easily leverageable and accessible across the ecosystem, or are these going to be just so expensive to train that companies that do have and have created those get a disproportionate advantage in terms of competition?
In terms of, you say why we are designing this special hardware, right? This is your question, right?
It requires that special hardware to compute at that scale to draw out that knowledge in any one of those. When you showed the newest models that you have trained, how do we think about them being available at a public level, at open source, at public scale?
I think we are doing this, right? So if you look at the AlphaFold model, is fully open to the public, and also some of the machine training model is accessible as open source at the Google Cloud.
We have another.
Hi, I have a question. First of all, thank you so much for your talk. So my question is that as the large-scale language models are becoming more developed, there is this notion of using natural language to produce code. Just as an example, for example, Microsoft worked on GitHub Copilot. What it does is that you can write natural language commands, and it converts those natural language commands into actually executable code. And approximately 40% of code, they did some study in small projects, was actually now being produced by GitHub Copilot.
Yeah,
So
I
now
know.
my question is that, first of all, is Google doing something like similar, or in general, how do you see the future of natural language commands or natural language, whether written or vocal commands, actually being converted into scalable, executable, reliable code?
Yeah, I'm not sure this. I saw it somewhere. So 35% of the software code can be written by machine now. So it's a job security for software engineers.
Did you get the answer?
And like that's true, but I'm just saying that is Google doing something similar to that where they
Yeah,
are
I saw. I think if you look at the web link I listed here.
Maybe the clicker.
I think you follow the links there, you will see a use case of Google's machine learning cases, and writing software code is one of the application. Yeah.
Another one. Go ahead.
Thank you. Talk. I was wondering what the smallest is do to run the prompt. Like if after you train the model, just execute it on smartphone.
You mean
Like train the model
Mhm.
and just want to use what kind of
machine we train on TPU, right?
come again?
TPUs. We
Yeah,
train
yes.
the models on 6,144 TPU chips.
Yes, for training, but also for running.
You mean the inference, right? Inference doesn't take a lot of compute power. Inference, you can do it relatively quickly. It's really the training of large models takes a huge compute power. All our large pod are used for training.
Okay, thank you.
Yeah.
Any other questions?
one
Oh,
more
there was
question.
more. Thank you.
I think I was nicely surprised to see how machine learning or your computer power was able to define something which is easier to understand than even human could try to define that way.
Mhm.
So that's very powerful, right? And
Yeah.
one of the things which I see, like my daughter, she comes back from the school and she says, I can't understand teacher.
Mhm.
And that's why the Khan Academy is successful, because they made it easier to understand.
Mhm.
Is there a plan to apply this kind of technology to make it easier for education of our kids? Because if they are able to understand a lot better,
Mhm.
let's say AI-based teachers rather than just human teachers, I think they will do a much better job, in my view.
Yeah. Is that a question or statement?
It was a statement, but
Yeah,
the
I
question
agree
was,
with- mhm.
is there something on your agenda, Google agenda, towards education sector as well?
Yeah, definitely. Yeah.
All right. Thank you so much. I don't think there are any more questions. Thanks a lot. Thank you so much,
No,
Hong, for.
here's one more question.
Oh, there is one?
Yeah.
Okay.
So this isn't really my field, so I apologize if this is a really basic question.
Uh-huh.
But so you had a slide that had a field programmable gated FPGA and
Oh,
or
yeah,
field
okay. Mm-hmm.
and a GPU and a CPU.
Uh-huh.
What advantage does the CPU confer that? Because the FPGA is like you can program it in the field. The GPU, the parallel processing, it's somehow better. But what does the CPU confer that the others don't do better?
CPU is a general purpose computer, so it has many small cores inside. It can do a lot of general things GPU and the TPU couldn't do. TPU is really optimized for large neural network model, so it has use different precision calculation, and it has a lot of memory around it, so you can do a lot of you can do training in a much efficient way than CPU and GPU. For the model we are talking about, like if you use the same for CPU, you have to use 10 CPUs and 2.5 GPUs, and we are able to accomplish the same computing in one TPUs. Yeah.
Thank you very much. Thanks a lot. Please put a big round of applause for Hong Lu. Thank you, Hong.